Hi, good afternoon, everyone. Any questions? Questions? Yes.
Will we use the final code for the draft code for 9A?
I don't remember.
Does the final what is the draft?
Oh, they do the same thing?
Yeah.
Yeah, then you should be able to do that, yes.
So just don't even change the final code, just use the draft?
Yeah, if you already have it solved, then yes, you're good. Other questions? Yes. 9A? Okay. This one here? All right, so let's have a quick look at 9A. Okay, well, someone asked if code check is down, so maybe it is. All right, so we're just going to try this by hand. Can I have a little bit less noise in the room? Otherwise, I'll say nothing. So let's pick a word. Like, what's everyone's favorite word? Like, word. All right. And so now we're supposed to do what? We're supposed to add a vertical bar in front and stick this into a queue. So here's my queue. Well, right now the queue is very short, right? So it only goes to here. So I have a queue where one string is standing in line to be served, and that's the string word. And now it says, while the queue is not empty, well, it's not empty right now, so that's a good sign, removes the element at front. So there's only one element at front. So I'll remove it in a minute. And then it says it has the form S vertical bar T. Does it have the form S vertical bar T? Well, it doesn't look like it, right? It has the form vertical bar word, but I guess these are symbols, and S is supposed to mean what? The stuff to the left of the vertical bar, and T, the stuff to the right of the vertical bar. So I have S is the empty string, and T is the string word. In fact, that's what it just says here. S is the substring before the vertical bar, and T is the substring after the vertical bar. For each letter C in T, how many letters do I have in T? I have 4 letters, right? W-O-R-D. For each letter C in T, I'm supposed to add S plus C plus a vertical bar plus T without C. That's what happens when you come late. So let's try it. We have 4 different possibilities. For each of the 4 different possibilities, W, O, R, and D, we're going to have to run through this. So let's do it for W. Then I get W, because S was the empty string, a vertical bar, and ORD, because ORD is word with a W removed. I'll do it for O, a vertical bar, and word, because word is word with the O removed. I do it for R, and then I get would, and for D, and would. So I get 4 strings. In fact, each time, well, I'm not going to get 4 strings each time, right? Because presumably T will get shorter later. So I get these 4 strings. What do I do with these 4 strings? See. Add them to the queue. It doesn't say in which order to add them, but I'll just add them in the order in which I found them. So now what does my queue look like? It no longer has word in it, but it has 4 strings. And what is the last one? D. So that's now what my queue looks like. It's now gotten a little fuller. If it keeps getting fuller all the time, that would be bad. So we'll see where that's the case. So now I'm done with this part here. That would be an easier way. So now what does it say? It says while the queue is not empty. Well, it's just gotten fuller, so it's certainly not empty. Take out the first word, that is W O R D. So this part here is S. This part is T. Now T only has 3 letters. So for each of the 3 letters, what do? It says I form S plus the letter plus the vertical bar. So we have W O, vertical bar, the O removed. We have WR, vertical bar, and the R removed. And we have WD, vertical bar, and the D removed. So I have 3 strings. What do I do with these 3 strings? I put them in the end of the queue, right? So now my queue looks like, well, I'm going to have it, so this one is gone because I took it out, and so I'm going to have it snake around the corner here a little bit. So in the next step, I would take out this guy here, and how many, now that you've seen it, how many new words am I going to get out of this one? 3, right? Because the string after the vertical bar has 3 letters. So I'll get 3 more in here. And so that'll repeat a couple more times. Eventually I'll get to the ones that have 2 letters behind the vertical bar. Each of them is going to give me 2. And yet, as you can see, the vertical bar is going to move further and further to the right. Eventually it's going to be all the way to the right. And there better be some clause in here. Oh yes, and it says, however, if the vertical bar is at the end, then you add it to the result. And that's eventually going to happen because it moves 1 step to the right every time. So eventually you're going to be finding these things in the queue that don't break out further, that don't give you further results. So do that once by hand with a string of your choice with 4 letters. Plenty of them. And just do it. I mean, obviously you're going to get 24 results in the end, right? Because there's 24 permutations of them. But go through the entire machinery by hand once on a long sheet of paper, or whichever way you want to do it. You might have fun with little Post-its. Put a new word on each Post-it and just stick them up in the queue. Whenever one of them is done, you just tear it up. You're going to need, 50 or so Post-its for that. That's money well spent. So that way, you will understand the algorithm and you will know how to do it by hand. Why do you want to know how to do it by hand? If you can't do it by hand, you can't code it, right? So make sure that you understand exactly how to do this by hand. And so it's good that you're asking right away, because in my experience, whenever I have to do one of these more tricky or intricate things, my brain takes a few minutes, hours, days to adjust to these things. So I like to do this first step, the do it by hand step, immediately when the problem gets published. Like, if you see it on Sunday, by all means, go out and get a sheet of scrap paper and just tinker with it, try to do it by hand. If you can, then you don't have to code until Tuesday afternoon, because the code itself is not difficult, right? If you think about what's difficult, what part is there to code? There's a couple of loops. The hardest part is to take the string apart. Okay, how do you take the string apart? Oh, substrings for sissies. Just use split. Split at the vertical bar, you get an array of two strings, right? So, so the programming of it is pretty easy, but you need to understand what you want to do. Questions about this? So really do this because it's a beautiful algorithm, and particularly the recursion haters are going to adore this. Right? Before we used recursion to do this, and now you can completely eliminate the recursion, because in a way what the queue does for us is it keeps track of all of the things that otherwise the recursion mechanism would have kept track of. It keeps all the partial work. And so in many cases, a queue is a really good way of storing partial work. So this happens all the time in data processing problems, that you do something and then say you want to have multiple processors work on it. You put it in a queue. You do a little bit of work, you put it in a queue, and then other processors or other computers can come along, take it out of the queue, move it to the next stage, put it again to the queue, and move on. So it's a very common way of organizing work. And so one always looks at a queue and says, now, what could it possibly be good for? But it really is surprisingly handy. Other questions about anything? Yes?
What is better in terms of performance and storage spaces than a queue or one?
Well, I mean, it's one like the other. Either you store the intermediate results on the runtime stack, or you store them in an external stack or queue. So if you have a smart card with 8K memory, either way it gets eaten out of those 8K memory. The only advantage of having this external structure is that the runtime stack tends to be more limited in size, because it has to be in one contiguous memory, whereas these queues could live on the heap and be as long as you like. But again, I mean, how many recursive calls do you have pending here? If you compute n factorial permutations, you never have more than n pending. Well, that might not be true. There might be more. I'd have to figure out how many of them are pending, but it's not enough that I'd worry about it. So don't worry about the performance and the memory. The question is, which way is the algorithm natural? And I think the algorithm that we had at first with the permutations was probably a little bit more natural than this one, at least judging from the various Piazza questions that say, what the heck is this supposed to mean? Other questions? Yeah.
I was going to talk about, or ask about the strike. Are you going to talk about it?
The strike. Oh, yes, I can talk about the strike. And as it happens, I was supposed to wear this T-shirt, but it was too tacky to bear. So I leave that to my colleagues. So we're 15. No, we're 7. Oh yeah, so I put this on the wrong thing. All right, so the deal is that so the faculty may go on strike. It may or may not happen. So I will certainly join if we do, and for a very simple reason, and that is that our salary is just so ridiculously low at this point that every day my wife says, "Why are you not returning the email from the Google recruiter?" And she is of course right, and I should. And so it's bargaining, and with if the faculty stick together, we will get a pretty measly raise, and if we don't stick together, we'll get no raise at all. So, will it happen? I don't think so. It's never happened. Like 6 or 7 years ago, there was a one-day strike at 2 campuses. And I think Cal State East Bay and Dominguez Hill. I actually drove to Cal State East Bay out of support. And because I had to do something with a tacky t-shirt. But, so I wouldn't really worry about it. Yeah.
When would it go into effect?
Oh, the raise?
I don't know, the strike.
Oh, you know, the raise probably the way things are going in 2039, but the strike, no one really knows, because there's fact finding, and I don't know when that is finished. It's a routine strategy for the union that they want to show strength, and so right now they're agitating for it, and probably a lot of faculty will vote for it, and it's perfectly possible that the fact finder says, you've got to be kidding, you can't give people a 2% raise over 3 years. And then maybe they'll fold, but I have no way of knowing. So it's not going to happen on final state. Yeah, whether that's good or bad, I don't know, but it's not. You'll know when it happens. All right, so no, I put this in the wrong thing anyway. Yeah, and so you'd say, is it a pain for the students or is it a good thing? I mean, in the long run, it's got to be a good thing if they pay enough money to make it so that one can hire competent instructors, because otherwise you're going to be taught by clowns that are worse than me. So, all right, other questions? Everyone is all clear with the other homework? All right, let's. One comment with this GitHub thing. So I was unhappy with the way that the GitHub classroom worked out. It appears that everyone can see everyone else's repo, and the GitHub people have not yet gotten back to me on how to fix that. So I will do one of two things depending on how much time I have on my hands. Either we're going to move it to Bitbucket, or we're going to wait a week. So I don't yet know, but it may happen that tomorrow I get bored and I'll move everything to Bitbucket, and then the final would have to be turned in through Git on Bitbucket. It still would be Git, but so be prepared for that possibility. I will announce it in time. I very much like the idea of using a version control system for your homework. It's the professional thing to do. The sooner you learn it, the better it is. It's something that you're going to have to be doing at work every single day. And so, and it really is a good thing for submitting all sorts of stuff. And once we get the bugs out, I could even make it so that you wouldn't even have to go to the code check web page anymore. You could just, on the command line, run a command that checks things out. And you wouldn't have to submit anything through Piazza anymore. And if, God forbid, your computer crashes, everything is saved in the cloud. So it would be a great system if we could get it going. I'm just, working on getting the bugs out. All right, so on to collections. So this sets. Am I in the right lecture? I am, right? Let me double check that out. What did Dr. Pierce talk to you about? Oh, he did 15.1 and 15.2, right? Yeah, all right. So, sets. So a set is a collection that's on order, where you toss in elements and they just get scrambled in some order. And you would say, well, why would you want it? You have a perfectly good collection to have stuff ordered, namely an array list. You put, or a linked list for that matter. You put things into an array list, and they are in order. The reason that you want unordered collections is that sets are much faster. If you don't care about the ordering, the data structure can put things in an order that's convenient for it. So, in particular, if you want to find things, suppose you have 5 million elements, and all you want to check is a particular string, say, among those 5 million. With a array list, you would have to go through all 5 million of them if they're not sorted, or if the array list is sorted, you would have to go by using binary search. You have to, 20 some lookups or so to get there. But a set can do much better, as we'll see. So a set makes a trade-off. It says, if you don't care about order, I give you more speed. There are two different ways of doing that, called hash sets and tree sets. And they both have advantages and disadvantages. The general rule of thumb is use a hash set if you don't care about ordering at all. A tree set sorts things by size, by whatever you say is the measure of size, and it's slightly slower to do that. But if you want to traverse things by size, then the tree set has an edge. So here, the picture that I have here is a hash code is some characteristic of an object. And so what I'm having here in this picture as the characteristic is like, the pattern of the spine. And all of the ones where the spines look the same, one puts together in what's called one bucket. So you have the white bucket, the blue bucket, the orange bucket, and here this other one. Whereas in a tree set, you would order them by size. And either way, that ordering makes it possible to find in this case, a book quickly. So it's easy enough to construct these things. You make an empty one by saying, make me a new hash set. You put it into, and that's the only thing that's remarkable here. It's considered good form to put, whenever you make a set, to put it into a variable of type set, so that at this point you no longer care whether it's hash or tree. And that way, A, it's shorter to write, and B, it shows that only the creation of it really involves the nature of the data structure. Everything else should work independent of that. And if you change your mind and you later say, well, for whatever reason, I want to change from one to the other, you only have to change one line of code. So you should always do that, and that's an easy thing to do. So with the tree set, I'm not sure we're going to run into this anytime soon, because right now we're just collecting strings and such. But if you have something that's, like say you have a collection of rectangles, you have to have some way of comparing them, and then you would put in a comparator, like we've seen when we've discussed comparators in the chapter on interfaces. So most of the operations with set are actually quite simple. They are simpler than with linked lists. You've seen linked lists with Dr. Pierce, where every time you wanted to do anything on the linked list, you had to get out an iterator. That's actually not quite true, right? Some of you have discovered that the Java implementation of linked lists, you also can do things like get and set like you can do for array lists, but that's actually very, very bad, and you should never do that. Why did they put that in? It boggles the mind. I have no idea. No other library does that, and when I talked to the guy who did it, he said, well, what if someone wants to do it? Who am I to prevent them from? But the whole point of a library is that you don't want people to do something stupid. Well, what can you say? So don't ever use get and set on linked lists. So when you use linked lists properly, you always deal with these iterators, and the iterators are nasty. They're nasty to use. They are nasty to implement, as you'll see next week. With sets, it's much nicer. So a set is a data structure, and you don't know where anything is in the set. It has no positions because there's no ordering. You toss something in it, and it's in there somewhere. You don't quite know where, and you don't worry about where it is. So you can add new things to it by calling add, like you see here. Notice that because it's a set, it does not have duplicates. So here I tossed in Romeo, and then I put in Romeo again, and it's fine, it's not an error, but it simply does nothing. So by the very concept of a set, it does not count duplicates. One could make a data structure that does count duplicates. Some libraries have it, but they're not very commonly needed. So if you want to find out whether the set contains something, you just call contains. So with an array, most of you have found out that you can use contains on an array list, because we've used it a couple of times. But with a set, that is the fundamental thing that you want to do, because it does not actually visit all elements. With an array list, contains has to go through all of the elements. With a set, because the way the internal data structure is organized, contains will home in on the right spot where if the element is there at all, it must be there, and it can give you an instant answer without having to look at all of the elements. So there's remove, of course, that's the opposite of add. And you can remove things that are not there, and that's okay. So over here, we're removing Juliet. Juliet was not in the set. It's not an error. It just quietly does nothing. Exactly like adding Romeo twice was not an error. It quietly did nothing. If you want to iterate through all of the elements in a set, you just use the generic, this enhanced for loop. So you say for all strings name and names, and then you do something with them, just like you would do for anything else. So you never use indexes because elements in sets don't have indexes. You just use this for loop. And that's pretty much all. These are all the basic commands that you have for sets. There's one thing that's a little tedious. What if you wanted to remove things that match a particular criterion? For that, you could use an iterator. So let's say you wanted to remove every word that starts with an R, like Roger and Romeo and all those. Then you could use an iterator like you've learned last week, but that's actually tedious, and in this day and age, no one does it. It's better to use the remove if method and pass a predicate. So here we're removing all strings that start with an R, and if you've paid attention, weeks and weeks ago I had these lambda expressions, the bonus slides on lambda expressions, and so here you find one. All right, so let's see if we can get CodeCheck to work. If not, yes. All right, so I want you to try this out. So here you have a program. The way that it is it's going to read in all of the words from Alice in Wonderland. You don't see that, but trust me, I'm feeding that into the scanner. And I want you to tell me how many unique words are there in Alice in Wonderland. Now, something you've always wanted to know. So how can you find out how many unique words there are? I mean, you could put them all in an array list, sort the array list, remove all adjacent duplicates, but that would take all day. With sets, it's much easier. You just put the first word into a set, you put the second word into the set, you put all of the words into the set, duplicates are automatically discarded, and then you find out how many elements are in the set. So, go for it. Oh, and I need to put on the clicker question to Piazza. Where is it? Okay. All right, so I'm making a hash set of strings here. So notice here it's a set of string. Over here it's a hash set. I don't have to repeat the type here. So what do I do for each word? So I add it to words, so that's in.next. And then I guess I'll print the size, right? And the suspense mounts. So now poor code check is overwhelmed. Oh, that's crazy. Okay, well, we'll wait out code check here. So it doesn't matter how many words there are, right? It matters what you do. So this is a trivial little program, and that's like a typical first use of sets. Here we go. And it was, well, no wonder code check's been working hard. It was 5,909 distinct words. Oh, but that's actually wrong. Wasn't I supposed to convert them to lowercase or something? So in that case, I should really call dot to lowercase so that I always force them in lowercase, otherwise they wouldn't get compared right. So if we do that, then I believe it'll be 5,472. So let's see how the voting goes. Okay, we'll find out, but it looks like most people made the same mistake that I originally did and forgot the to lowercase. So I just added that in as an extra twist. It doesn't much matter for understanding the concept, but you get the idea of how to do this. So you toss these words in a set, you automatically get rid of all duplicates. It's a beautiful thing. All right, so the next thing I want you to do is, it's another coding question, hopefully with less work on poor code check. Oh dear. Okay, this one is done. And sure enough, here it's 5,472. Here we go. All right, so the method that you're supposed to write is a method that you would imagine has to exist for sets. Right, so if you have two sets, I want you to compute the intersection of the two sets. That's, as you remember from, I guess, your discrete math course, that's the elements that are in both sets together. So I want you to write it in such a way that you don't mutate first and second, but that instead you return a new set that contains every element that is in the first one and in the second one. And there is this thing that says, what is the laziest, simplest way that you can do that? Right, that's what it says here. So, can you do it with 1 or 2 for each loops? Can you do it with iterators? Is there some nifty method or maybe a combination thereof from the set interface? So it would be really helpful if you pulled up the set interface really quickly. Unfortunately, there's way too many sets in here. Tree set. So here's the set interface, and you can see it has a bunch of methods that may or may not be useful. So feel free to discuss it with your neighbor for a couple of minutes, come up with a strategy. Oh, it doesn't give us the, oh, never mind. So, so that's probably a straightforward way of doing it. So I could say, all right, what set do I use? Hash set or tree set? Hash. Because that's what they said. If in doubt, use a hash set, okay? And now I could certainly do the following. I could go through each of the elements in the red set. And that's a simple loop. And for each of those, I could ask, is it in the green set? And if it is, then I add it to the result. And otherwise, I view it with scorn. So, what's the green set? Second contains E. And that would probably work, right? So let's see. So this would be the choice where it said I used one or more for each loops. Let's see what most of you did. And that's actually not what most of you did. So most of you used methods from the set interface without any loops. So is there an intersection method? Add all, contains all. There is actually no intersection method here, so it can't have been that easy. But there actually is a way of doing it. If I could just get this to come back. Gosh. Is it always this slow? Oh yeah, here. And I passed my test, so I'm good. But let's do it the other way around because that one is more fun. So here what I've done is, I've done the obvious loop, but the nicer way of doing it is to say, well, I want to use one of these methods. So which methods would work? And so remove all, that doesn't really work because if I start with the red set and then I remove the green set, then I get this stuff here, which is exactly the opposite of what I want. But the winner here is retain all. Retain all retains all the elements in my, so if I say first retain all, second, then it'll get exactly the yellow ones. It'll throw away everything that's not in the intersection. But I'm not allowed to mutate. So the first thing I have to do is I have to make a copy. So I make a copy, and then I call retain all on the copy. How do you make a copy? You construct a new set, and in the constructor, you put the old set. This makes a copy of all of the elements, and this works with any collection. It's a useful thing to know. So here I'm making a copy. Then I call result retain all second. And then I return call, yeah. And that's certainly nicer and prettier. And so I'd recommend to do it. It only requires that you are able to parse these library classes quickly. So let's see what you guys did. And so a lot of you did that, and that's good. You know, a bunch of you wrote a for loop, and that's certainly fine. A bunch of you say that you wrote an iterator. That's actually hard to do. How the heck do you do that? I guess you could, right? You'd have to write so you'd have an iterator. And so then that would be first.iterator. But then what? Now you can see all of the, I guess you can now do the same thing as you've done before. And then say if a second contains X. So that'll work, but it's ugly. It's more complex than the for loop. So there's no good reason to do it. So as a rule of thumb, if you find yourself using iterators with sets, you're almost certainly not doing it the best way. The only reason that you might imagine is because you want to remove something, then I guess you do need an iterator. Do I have a question about that? Yes? Oh, come on. So, while it's waiting for this, so the reason that here the iterator didn't buy you anything over the for loop, and I'll write the for loop under it so you see the two together. No, the for loop was for integer x colon first, is the for loop does everything that you want. It goes through all of the elements in turn, just like the iterator does. And so iterating a step at a time doesn't buy you anything but clutter. There's one thing that the for loop cannot do. You cannot use the for loop to modify the data structure. So if you wanted to remove something or insert something, well, insertion, you don't need an iterator anyway. It's a set. The set has no order, so you always toss it into the set. But removal, you might want to look at a particular element and say, I don't want that one. And that is what this exercise is after. We may need to skip this if it's not loading. Okay, we'll look at it here from. So here I want you to change a set, and this one you're allowed to mutate it, and I want you to remove all even elements. So in other words, you only have the odd ones. And I think we're going to give CodeCheck a break, and I'll just tell you what I had in mind. So here, it is possible to use an iterator. So we would say iterator integer iter equals numbers iterator, while iter has next. If, oh, then I have to fish out the next first. And now if x is even, then I want to kill it. So if x mod 2 is 0, then I remove it. Oh, so how do I remove it? So can I write numbers remove? What happens when you do? What happens? Let's see what happens. Yeah, that's why I wanted to do it on CS20, because this is a bug I haven't fixed on the other side. Let me try this one more time. All right, this is hopeless. So if you try it like this, you're going to get something very strange. You're going to get a concurrent modification exception. Did anyone ever get a concurrent modification exception? You will soon. So here's what happens is we're looking at which set? We're looking at the set A, and so here's my iterator. Pointing, say, here, and it keeps on moving through. And the way an iterator works is, you'll see that next week, it remembers the place at which it was at. And so it knows what goes on inside that data structure. And the data structure has some sequence of these elements. And now when you remove something from it, or when you add something to it, then the iterator may no longer point to the same place. And what the iterators do is they check whether the collection has been changed since they started iterating over it. And if the collection has been changed, then they throw this concurrent modification exception. So you can never add or remove something in a collection that you're also iterating over at the same time. The iteration will then fail. So what's the remedy? So if I can't call numbers.remove x, but I still want to remove the even element x, how can I remove it? No. I mean, it's an opaque data structure. I have no way what goes on inside it. And the implementation is actually if these things change once in a while. Well, as Dr. Pierce told you on Wednesday, that an iterator itself has a remove method. Did he talk about that? Okay. So you can call iter remove and that removes the element that the iterator has just returned. And so this way it'll work, then the iterator knows how to deal with the internals of the data structure. All of this will make a lot more sense next Monday when we're going to be looking at how these things work inside some data structures. So this is a feasible way of doing it, but I've always hated this way because I always thought it was that it's the most unintuitive thing. So what you're doing here is you're going over this thing here, an element at a time, and this call to remove is, please, Mr. or Mrs. Iterator, remove the thing that has just been returned by next. And it works, right? You can do it like that, but I've never found it particularly intuitive. So my strong preference when coding up something like this is to use remove if and to simply say numbers remove if, and now put in the predicate that you need to test whether a number is even, and that's of course just it's easy, it's short, it's simple, and so that should motivate you to master these predicates. It's not something we'll ever have in an exam in 46B, but if something like that helps you, 10 minutes of labor and a homework, why not? It's legal Java.
Can you explain lambda?
No. So right now you're going to have to learn lambda by assimilation. That's like a baby learns in a new language. You look at it and you see it obviously makes sense, right? So this thing here tests whether x is even or not. So it eats an x and it returns a true or a false. And it returns true if x is even and false if x is not. So if you had to remove all odd ones, you would know what to do. How would you remove all odd ones?
X mod 2 equals 1.
Oh no. So he said the odd ones you do it like this. What's wrong with that? Well, what if x is negative? What is minus 3 mod 2?
1 more negative.
Stupidly, it's minus 1, and so you can never do that, so you have to say not equal 0. That'll work. Yeah, this is a nastiness in Java and C and C++, because the mod operator is badly defined for negative numbers. All right, but still, the point here is that remove if is different. All right, moving on from sets to maps. So sets are occasionally useful. Maps, on the other hand, are the single most useful data structure ever. So years and years ago, I read in some book about programming in C, where the author's name was Peter van der Linden. He said that if he was stuck on a desert island with only one data structure, Lord, please make it a hash table. That's a map. So, and that is the honest truth. So maps are the single most useful data structure ever. So what's a map? A map associates keys with values. The keys can be anything at all. The values can be anything at all. So here we happen to associate strings with colors. And every string is associated with exactly one color if it's present. And some colors, of course, may be the target of two different strings. And it's a very simple concept, and it'll grow on you just how useful it is. Using maps is pretty easy. There's tree maps and hash maps, just like there are tree sets and hash sets. A map has two types. It has the type for the keys and a type for the values. So here we have a map that maps names to scores. In the previous picture, I might have had a map from string to color. I put in elements by calling put, and I give the key and the value. I can update a value. So if Sally's had originally 95 and now she found out that the professor didn't grade the exam right, now it's updated to 100. I can read what the score was, or what, in general, what the value of a map was with the get method. The get method returns the value that's present, or it returns null if there was no association. So if I have a map of colors, then null isn't, that's just a normal object reference. You have to be a little bit careful when you have a map where the value type is a primitive type, integer or double. In that case, if you want to take care of the null case, make sure to cast this thing here as an integer, not to cast, but to declare it as an integer, because an int can never be null. An int is a number, it's a primitive type, and then you wouldn't be able to detect the null. So if you wanted to iterate over a map, which sometimes you have to do, can we have a little bit less noise up there? You iterate over the set of keys, and for each of the keys in the key set, you call get to get the value. There are other ways of iterating over a map, but this is the simplest one. And finally, what if you'd want to remove a key? You just remove it with remove. You don't have to specify the value. Both the key and the value are removed. So, now I want to find out how many words in this input have length 1, how many words have length 2, and so on. So I'm having an input file. I don't remember what it is. And hopefully code check will have recovered by now. Nope. We'll try this. All right. Same loop as you've seen before. So try the same. You can just replace the CS20 with codecheck.it and drop the colon 8080. I'll leave this open so you can do that. And so now we want to, so let's say we had Mary had a little lamb. And I want to know how many words are there of length 1, of length 2, and so on. So the way to do that is that we will make a map from integers to integer. And now let's say we read in Mary. At that point we have found a string of length 4. And now we want to increment the counter of it. So I would want to say something like this. See, I only care about the length of the word. I just put it in len. And oh, I need that map, huh? I'll call it lengths. Okay, I'll make it a hash map because I can. So now what I want to say is, and I'll give you this for free, the rest I'll let you figure out yourself. So what should I put into the entry for len? I guess I could put 1 because I found 1, but that doesn't really work the second time around, right? The second one I want to increment to 2. So I can say lengths.get 1 plus 1. That way I would increment it. And in the end, I would just print all those lengths. So let's run through it again. Let's say we just had Mary and lamb. So let's say we already read in Mary. And after that, of course, the counter for 4 was 1. And now we're reading in lamb. So len is again 4. So now, oops, not get of 1, get of len. So I'm getting the and I shouldn't call them lengths. That's a stupid name. How about counts? So I have the count of the ones that are length 4. I'm getting those out. That was 1 previously. I add 1, so now it's 2. And now I'm putting it back, so now the entry of 4 will be 2. So that's the basic strategy. There's just one catch, and that is that it doesn't work. Otherwise I wouldn't have told you. So I'm getting a null pointer exception. Why? All right, so discuss that with your neighbor and fix it up. So I guess right now I have to answer 4 in Piazza. Yeah. Oh, he had a tree map. So where's the null pointer exception come from? Yeah. Yes. So, as with so many other things in life, with maps, the first time is special. So, when you put something in there the first time, there was nothing in there before. And so, in that case here, so let's say we read the very first word. We read Mary. Length is 4. So we're now calling counts.get of 4, and we're getting null. Right? There's nothing in there before, and so null can't be cast to an integer, and so there's the null pointer exception. So how do we fix it? You need to somehow find out, is it the first time? So we could ask Mary, right? But no. So what do we do? So you really have to make a case for that. So you have to say if counts.get of length equals null, that's the special case. What do you want to do in that case? You could do that. So there's two different ways of doing it. So what he said is, well, let's put in a 0, because then the next line will work. It'll fetch the 0 and add 1. And the other way of doing it is you say, well, in this case, we'll just put in the 1, and then we put in an else for the other case. So for some reason, I prefer that. I don't know why. Put length. So that's the first time. And else, and all the other times, we do the normal thing. And so this is something that you will commonly need to deal with. We'll be having all sorts of exercises with maps over the next few weeks. And so just always remember, the first time is special. Let's see. All right, so we have a bunch of people who never got past the null pointer exception. And probably many more people are still waiting for Piazza. So I have no idea how many words it actually was. But the important part is remember this loop. I'll bother you about that multiple more times because it's just such a common thing. All right, where's... Okay, so we're not getting to these hash functions, but it's not a big deal. You can look at those slides here for the homework where you have to do a hash function. So do yourself a favor and figure out in preparation for the homework what the hash code of this strange string here is. That's all I've got, so I'll see you on Wednesday. Still got null pointer exception. Oh! Does anyone want a USB stick? USB sticks?
So, Professor, I have a question about the draft day. Does that just mean the same as the